Hey everyone, I'm making this video to talk about common battery manufacturing issues. This is going to be part of some sort of series of videos to talk about the most common ones. Specifically, this one is about SOC imbalance, state of charge imbalance. And the reason why I wanted to talk about common battery manufacturing issues is that I've seen that there are a lot of engineers in the plant who have many years of experience in manufacturing, but it's the electrochemical manufacturing part of battery is not something that they understand really well. So even though they have really in-depth knowledge and a lot of experience, they cannot seem to ramp up the product effectively because they'll run into like very debilitating issues that are just not solvable by common manufacturing principles. So actually in this slide, the first thing I wanted to go over is actually all the text in the bottom left. So there I have it labeled as extremely important battery manufacturing fundamentals. Um, and then you're treating the cell like a resistor in this case. So the first principle here is that parallel elements must be at the same voltage. So that means all cells that are connected in parallel, they must be at the same voltage. And by connecting in parallel, I mean the positives are welded to the positives are welded to the positives, and so on until you get to all your cells. And all the negatives are welded to all the negatives, and so on and so on. So all the positives are welded together, all the negatives are welded together. When cells are joined in parallel, they actually naturally balance each other out. So, for example, you can have two cells, one a little bit lower at 10% state of charge, and one a little bit higher at 15% state of charge, 3.5 volts-ish and 3.53 volts-ish. And if you weld their positives together, nothing will happen. They'll stay at 3.5 and 3.53. But the moment you weld their negatives together and complete the parallel circuit, the 15% cell will actually charge the 10% cell up, and both will become 12.5%, which is like 3.510 volts-ish. So that actually, there's another point is you don't want to parallel join two cells of extremely different SOCs because the balancing current is not actually super well regulated. So you could overheat the cells and cause degradation. For example, if you parallel weld together a cell that's like 80% state of charge and a cell that's like 20% state of charge, that could cause some damage there that you are not really aware of. So that's the first principle. Parallel cells, parallel elements, they must be at the same voltage. Now the second principle is that series elements do not have to be at the same voltage, and there's no natural balancing that occurs. And by series elements, I mean cells that are in series with each other or cell groups that are in series with each other. Um, so balancing is actually artificial and has to take place over long periods of time via the battery management system algorithms. So what the battery management system BMS will do is it will use bleed resistors to bleed out the current, bleed out the capacity in strings that are a little bit higher, in series elements, series cells that are a little bit higher. But the problem is bleed resistors are actually quite fragile, and a lot of the times bleed resistors are what leads to thermal incidents. So they are usually regulated to do very small amounts of discharge over time. So typically 10 to 100 milliamps of discharge. And because there's no natural balancing before a BMS is hooked up into the system, this has significant manufacturing quality implications because it means that like you cannot just naturally balance the part out. You have to actually do first in, first out, FIFO principles really well. That will be discussed later. And the third principle is that parallel elements, parallel cells, they divide the overall circuit current. So let's say you're putting in 500 amps discharge. You're discharging 500 amps away from the system, and you have 4 cells in parallel. That means that every cell is getting about 125 amps of discharge. They're dividing the 500 amps, but they don't have to each receive the same current. And the reason why is because if a cell is high resistance, it receives less current. If a cell is low resistance, it receives more current. And the reason why this is true is because of Ohm's law, V equals IR. If your R is higher, your I has to be lower because IR are proportionally related to each other. And the last principle is series elements, so series cells or series groups of cells, they each receive the same overall circuit current. So let's say instead of 4 cells in parallel, you have 4 cells in series. It's just positive welded to negative, positive welded to negative, positive welded to negative, and you have 4 of these cells. Actually, in this circuit, if you discharge 500 amps, every single cell will be discharged by 500 amps because they're in series. So these are the 4 very basic but very extremely important battery fundamentals to understand. Now in the bottom right, I wanted to go over this curve. It's called the OCV SOC curve. This is like the main reference table that all battery engineering is based off of. Like this is the most fundamental table there is, and basically what this is it tells you what the resting voltage, the open circuit voltage, which is the voltage over an infinite period of time, is for a specific state of charge. So let's say a cell, you charged up 50%. You charged up from 0 to 50%. Now after an infinite period of time, your open circuit voltage should be around 3.68, 3.69 volts-ish. And that's basically, this is the main reference table that everything is based off of. If in this case, if you discharge the cell fully to 0% and then you waited like 3 days or something, you should see 3.31 volts, 3.310, 3.305 volts ish. And if you fully charge the cell, you should see maybe 4.15 volts ish over a very long period of time. So this is the OCV SOC lookup table. And then I basically wanted to go over an example in the diagrams on top of how an SOC balance can actually be very bad for the final product. So the first column of diagram is where I'm showing cells coming in. So let's say you have a bunch of cells coming in at 10% state of charge. They're all around 3.50 volts-ish. And then you put them in parallel, and then you have 5 groups that are in series, and then you put these groups in series. But one of your groups actually is at super low state of charge, like 3.5%, that red one that you see there. Like let's just say those cells were picked up out of the back of the manufacturing plant where they had been sitting for 180 days in a very hot part of the plant, and they were just sitting there for 180 days, and then someone just grabbed them and, oh, we should just use these cells, so let's just put them into the line. But they're actually at 3.5% state of charge, and they got put together in parallel, and then now they're in series with everything else. Well, because there's no natural balancing for elements that are in series, this is actually long-term how it looks. You're going to have 4 series groups that are at 10% and one that's at 3.5%. And the reason why that's such an issue is if you look at the middle picture, actually if you charge this pack up, what's going to happen is 4 out of 5 of your series groups are going to hit 100% state of charge because they're perfectly balanced with each other, or pretty much perfectly balanced with each other, around 4.150 volts. But because that every single element in series is receiving the same current, that one that's low can only get to 93.5 when everything else is at 100. And you actually can't specifically charge this 93.5 one up because everything receives the same current. So if you put in a current into the circuit, the 100% are going to go over 100%, which is not safe. So now this one is stuck at 93.5. And then let's say you discharge it fully down, the one that's at 93.5 will hit 0% first, 3.310 volts-ish, but everything else is stuck at 6.5, and you can't discharge anymore because everything receives the same current. All the groups receive the same current in series. So if you discharge it, it would go below 0%, it would be unsafe. So on the very right side, that little bit of text that's green, orange, and black, I'm basically explaining how if everything was perfectly balanced, if all 5 of the groups of cells were perfectly balanced with each other, there would be 332 watt hours at the top of charge, and the bottom charge, there would be exactly 0. So there would be 332 watt hours of usable energy. But in this case, because there's one that's 6.5% lower, it's only at 325.7 watt hours at top of charge because you're missing a little bit from your 93.5% one. And then at the very bottom of charge, you actually have 14.4 watt hours, and you can't go any lower because there's 4 series groups that have a little bit higher. It's still at 6.5. It can't fully go down to 0. And because of that, you actually lose 6.2% loss of usable energy. And the reason why this is important is because at beginning of life, you could actually fail EPA regulatory tests because you have less usable energy than you're supposed to. So that's why this SOC imbalance is really important to avoid. So if you remember in the previous slide, for that group of cells where there were 4 cells in parallel that were really low. I said, as an example, what if they were in the back of the manufacturing facility or somewhere and they were like 180 days old, super old? That's actually here, I'm talking about failure mode, so that's actually the first failure mode I wanted to go over. Failure mode number 1, open circuit voltage, resting voltage over an infinite period of time, degradation with age. So what I'm saying here is as cells sit at rest, their OCV actually naturally degrades at a certain rate. Usually it's very, very low. It's less than 0.1 millivolts per day. And usually it's the rate is a little bit higher when the cell's first manufactured. And over time, it kind of like the rate lowers and lowers. So it loses less and less per day. But it does lose a little bit per day of charge, just naturally discharging because of like entropy and things like that. So for example, if a part such as a module is kicked out of line to repair because it's failing some kind of check, if there's no robust repair process, it could literally sit around for months, right? Let's say it just gets put into like a pile on the side and everyone forgets about it. It's months, like 90 days, 120 days, 180 days. This could lead to the cells inside the module losing a few millivolts before being reintroduced. And because a module is usually many cell groups in series, you just multiply by how many series elements there are, how many groups there are. So let's say there's like 20 cell groups in series within the module. If you lose 3 millivolts per cell, you're gonna lose 60 millivolts in the module. So the module could even lose up to a few hundred millivolts before being reintroduced. And this is going to be a big issue because if you remember from the previous slide, the OCV SOC curve, a few hundred millivolts is like 5 to 10%. So that's a huge amount of difference. And then, if you put that into a pack, then it's going to like limit the amount of top of charge and bottom of charge. It's going to hit the limits faster because it's not balanced. So the fix in this case is to just charge the part, whether it's a module going into a pack or a cell going into a module, just charge it back up to the appropriate open circuit voltage and reintroduce it to the module or pack. But there's a concern here actually because OCV degradation with age is actually something that's OCV degradation is reversible, meaning you can simply charge it back up and it looks fine. But there's something that is irreversible. It's capacity fade. Not only does OCV decrease over time, capacity decreases over time as well. And this is also known as irreversible capacity loss, meaning the cell at one point it was 4 amp hours, but since you sat it around for 180 days, the cell got older and older. So now it can only hold 3.98 amp hours or something like that. So there's a capacity fade and irreversible loss associated with age as well. But the problem is you can actually mask this by charging the cell or module back up to the correct OCV before reintroducing it to the module or pack. And the reason why is because let's say you have something that's 1,000 days old, a cell that's 1,000 days old, and now the cell's total capacity is only 3.8 amp hours, whereas a brand new cell, the capacity is 4 amp hours. So you can actually charge a new cell and a very, very, very old cell up to the same OCV, and they will look the same instantaneously. But actually, the one that's at 3.8 amp hours has much less capacity. So the solution to this is you would set an age-based limit for the part based on its traceability in the plant. So you would set an age-based limit past which the part must be scrapped. And then you would use, the reason why you would have this is to avoid a lipstick on a pig situation, where it's a very, very old part, but you basically charge it up so it looks like new. You want to avoid those situations because it's going to limit the amount of a capacity that the customer can get. Because for example, in the previous situation that I showed on the last slide, if you're instantaneously, your SOC is a little bit higher, you're going to have behavior like this, where you're hitting the top first and you're hitting the bottom first. But over time, those bleed resistors can actually bleed the one that's high up and it bring it more balance. So now it's balanced over like a month or 4 weeks or so. But if you have something that's capacity faded, a very large loss in capacity, what will happen is even if you're completely balanced, when you put it into the pack, it's going to hit the upper limit first and it's going to hit the lower limit first. It's going to behave like this, where it's not like in line with the rest of them like it was previously. It's actually going to be less capacity, and then that's actually another concern entirely. So let me go over second failure mode now. Second failure mode is open circuit voltage. degradation from cell internal short. So this happens if the supplier is sending a cell where, for example, the cathode and anode is shorted. It's not separated properly. Like the ways this can happen is like if they over voltaged it during the formation process, and then now there's like lithium buildup on the anode, and the dendrite is poking through the separator. It's like a little finger that pokes through the separator and touches the cathode, and now it's shorted, and the cell is losing voltage, it's losing capacity. It could also happen if the supplier plant is dirty, like it's not a clean room and there's metallic debris inside the separator, inside the anode, and it's like when they like push it together, it's like it punches through and shorts the cell. There's other things like if there's uneven wet out of electrolyte, it could cause current to like flow very strongly in some places and not as much in other places. And then current disuniformity is actually one of the big contributors to causing dendrites too, because the more current that goes somewhere, the more chance there is for dendrites to form, for lithium plating to occur. So all these things are supplier issues, and the fix for the part is you either replace the cell or you scrap the part if it's already welded. So the third failure mode now is OCV degradation from an external short. And the ways this can happen is like, for example, there's like a natural flow of current throughout a module. It's just like a pathway, but if you accidentally bridge that pathway and create a shorter pathway, that's what a short is. So let's say you touch a screwdriver from one end of the module to the middle of the pathway. Now the current will all flow between that screwdriver because it's super low resistance. It's going to flow there, and then it's going to cause the screwdriver to heat up, and it's going to do a big pah and a big arc. It's going to be like fireworks everywhere. So that's one of the ways you can short a module. Someone touches a screwdriver to the module in the wrong place, or your tooling controls are off during the manufacturing process, and it's more of a systemic issue where the tooling is like shorting every single part during assembly. Like for example, if there's like a robotic arm that's like grazing the side of the module and touching something else and causing a short there. The fix for this is there's no fix. You cannot control the amount of current that's passed through an external short. It could be thousands of amps. It's very, very unsafe. You're going to hear a loud boom. You might burn your hand or burn the screwdriver. There's no fix. The part must be scrapped. And then the bottom part, there's a common misconception that I have here that I see a lot of engineers have, where they think that they can get rid of an SOC imbalance by charging a module to a set voltage. This is actually untrue because I explained earlier, series elements, they receive the same current. So if you're already off balance in the beginning, everything's getting the same current. You can never eliminate SOC imbalance within a module until you connect it to a BMS, which will bleed the higher voltage series elements over time. And I have a last slide here to talk about SOC imbalance. I basically wanted to drive it through the PFMEA because to me, the PFMEA is what every single defect in the manufacturing plant should be driven by. It's process, failure mode, effect, and analysis. So in the PFMEA, there are three categories. There's a severity category, which says how dangerous or how severe a defect is. There's a detection category, which tells you how difficult it is to detect. If it's impossible to detect, it's a 10. If it can be detected every time, it's a 1. And then the last one is occurrence, which is how often does it occur. And this one is a little bit dependent on the company that uses it. They will define it differently. But basically a 10 would be like it occurs like over 1% or over 10%. And then a 1 would be like it only occurs once every like 10 million parts or something like that. So the first failure mode I have here is SOC imbalance due to age, failure mode number 1 from the previous slide. The severity here for this one, as it is for all of them, is 8. And 8 is 100% product scrap with no dangerous effects. If you start getting into a dangerous failure mode, then it will be a 9 or a 10. But the reason why this is 8, 100% scrap is because if you have an SOC imbalance outside of the acceptable limits, it leads to regulatory failure because the EPA will do a beginning of life test on the pack and you're going to fail it because you're hitting the top limit first, hitting the bottom limit first, and now you're losing a lot of usable energy. So that's why it's a high severity issue. Detection wise, I have it at a 3 or a 4, and 3 or 4 is basically like you can detect it pretty well, but 3 is like you'll detect it in line with the equipment, like it'll be kicked out, and a 4 is like you'll detect it, but it'll only be detected after the test, so it will be detected during post-processing. And the occurrence, I have it actually at a very, very broad spread, 1 to 10, because it's really highly dependent on what the plant does in respect to first in, first out principles. Like you send a part to the line, they need to consume it first before they consume another part, right? That's first in, first out, but a lot of companies don't do this very well. And the other term for this is hand to mouth. It's you whatever you grab first, you eat it first, hand to mouth. It's also dependent on operator handling. How do people stack pallets? If you have like, for example, cells that are like just you stack like one pallet, but then that's actually at the very back. So the more you stack, the less likely you are to get to it. That's an example of like a poor FIFO and handling procedure. So the key takeaway I have for this on the right is that the SOC imbalance due to the age, the risk priority number, RPN, which is the severity number times detection times occurrence, is heavily dependent on FIFO procedures and other various sorting procedures at the plant. Poor handling practices will lead to a completely unacceptable RPN where almost every single module is like you just have no idea like what kind of SOC it's at. Or the cells, they'll just be totally spread SOC, whereas an excellent FIFO will lead to a super low RPN because you know that all the parts are being consumed as soon as they're being received, and there's no issue. There's no need to fix anything. The second failure mode is SOC imbalance due to a cell internal short, a soft short. For this one, severity is 8 because if you fail SOC imbalance, you have an opportunity to fail the regulatory to fail regulatory energy as well. But the detection I have here is a 3. It's a little bit lower. Detection is a little bit better in this case because if there's a cell internal short, it should be caught very early during the incoming cell check from the supplier. Occurrence, and I have this at a 1 or a 2, it's very low because typically suppliers are sending good cells. It's cell suppliers are never looking at like 10%, 1%. They're looking at like 0.0001%. They're looking at like very small increments like that. So the key takeaway is that SOC imbalance due to cell quality, internal short, soft short, the RPN is extremely low, and you could actually reduce this even more by doing periodic supplier quality audits. Just every once in a while, you run 1,000 cells through your incoming check, and then you see, oh, how many of them fail? And then you compare that to what the supplier is telling you that you should be getting them at. And then the last failure mode, SOC imbalance due to cell external short, a hard short caused by like a screwdriver arcing something, or the tooling is like arcing the module. Severity is 8. I didn't actually include the hard short itself. That would be a 10 because that's very dangerous. But I'm just talking about the SOC imbalance due to the cell external short, and that severity is the same as the other ones. It's just 8 because you can fail EPA testing. Detection here I have as a 1. It's very, very detectable. And the reason why is because an external short, which is caused by equipment or operator, like I was explaining earlier with the screwdriver, it will lead to unavoidable audible and visual cues. Like there will be a bang. The part will be covered in soot. It will be black. Like the part will be completely blackened. It will look like there was smoke there as well or something like that. And it will also lead to significant SOC imbalance that would be easily caught at any stage of production because, like I said earlier, you're passing thousands of amps through the part. So there will be a very high SOC imbalance. And then the occurrence is 1 to 3. It's very good. Occurrence is usually for this is very low, and then it really depends on operator handling and tooling. The key takeaway is SOC imbalance due to external short, RPN is extremely low and may be reduced by providing insulated tooling and training operators to not contact certain parts incorrectly because it could be causing an external short. And then the last point I have here is actually one of the interesting nuances that I've learned over time at the manufacturing plant is that it can be extremely difficult to distinguish between OCV degradation in a module or a cell due to an internal short which may be acceptable up to a certain point. For example, if your module has if your module has like 48 cells in parallel, negative to negative, positive to positive, parallel, you could like maybe have 1 or 2 cells with an internal short and still meet the specification. But if you have like 3, it might be unacceptable. So that's why I wrote may be acceptable up to a certain point. But it's actually very difficult to distinguish between an internal short and an external short that's caused by an external factor, a hard short, because this actually is never acceptable, because you have no idea how much current was passed, you have no idea if the cell is damaged or not. It's completely unacceptable to accept this kind of part. So one suggestion that I have that I've found is helpful is to check the DC internal resistance of the series elements of the module with a current pulse. So this is basically checking the internal resistance of every group of cells. But this can get really muddied the more cells that you have in parallel, because parallel resistances are added together. So you might see like 50 cells worth of resistance, but one is like really, really high, but you won't be able to tell. So actually, my primary suggestion is actually to just address the supplier quality, keep a good handle on that, and then the plant handling, with the operators and with your tooling, you also need to address that very, very proactively. And then once you do all of that, it will push a current score so low that you can safely scrap all the failures, because it can be very hard to distinguish. So the correct thing to do, really, in my opinion, is to scrap all the failures. But if the occurrence is high, then that won't be palatable to production team. So you actually have to be very proactive in order to take the safe route here.